So I did want to go ahead and start our transition to our next unit, which is applications of derivatives, uh, by actually revisiting limits. Because uh, when we talked about how different ways of evaluating limits, I said, hey, there's one step that's kind of right in the middle of the things we try that we haven't learned yet and that needs to wait until we learn some more material. Well, now that we've learned about derivatives, we can address that, and that's called L'Hopital's rule. So in L'Hopital's rule, to kind of go back to this, the ways we evaluate limits, we always try substitution first because 90% plus of the time that's going to work. If that doesn't, we try simplifying algebraically and substitution again. And then I said we've got this L'Hopital's rule, and I put little stars by it, not because we didn't know how to do it yet, but because L'Hopital's rule can only sometimes be used. And then graph or table, and finally sandwich theorem if all else fails. So L'Hopital's rule itself. Uh, L'Hopital's rule can only be used for limits that approach what's called an indeterminate form. Please note I'm saying approaching, not equaling, because the idea here with L'Hopital's rule is that we always have to talk about approaching, not equaling. So the two that it's really designed for are when we have limits that approach 0 over 0 or a positive and negative infinity over infinity. Other indeterminate forms that L'Hopital's rule can be used for but are not covered by the AP exam, if our limit approaches 0 to the 0 power, or infinity to the 0, or 1 to the infinity, or infinity minus infinity, or infinity times 0. And this is one of the reasons why I say approaching is a really important concept here, because you may be saying, well, anything times 0 is 0, but we're saying an infinitely large number times an infinitely small number. So we're not saying times 0, we're saying times something that's getting close to 0. So it's not quite 0. And that's where the behavior can get strange. If there's time in the classroom, we will look at some of these so that you can just get exposed to them. But you will definitely see this on the AP exam with limits that approach 0 over 0 or positive or negative infinity over infinity. So this is specifically for those, in AP's cases, for these two indeterminate forms. So we're dealing with rational functions here. In other words, we have a function in the numerator, a function in the denominator. It says if we have limits that approach this, we can instead say, well, in an indeterminate form, it's called indeterminate because we can't determine what that actually equals. It might exist, it might not. We can set up an equivalent limit. So the limit as x approaches a of f over x divided by g over x, if that approaches an indeterminate form, then L'Hopital's rule says that we can set up an equivalent limit as x approaches a of f prime of x over g prime of x. So we're being given an equivalent limit. It doesn't find the limit, it just says, hey, let's try this different limit instead. Another thing to note, this is not quotient rule. We're not taking the derivative of the entire function, we're saying the derivative of the top compared to the derivative of the bottom. What it really is if we don't want to look at this as a quotient, we want to look at this as a ratio. So it's the limit as x approaches a of f of x compared to g of x will be equivalent to the limit as x approaches a of f prime of x compared to g prime of x. So our general approach with this is when we see a limit, we first want to try substitution. And we want to show that our numerator and denominator are both approaching 0, or they're both approaching one of the infinities. Positive or negative doesn't matter. It's just both numerator and denominator have to approach one of the infinities. They don't even have to be the same infinity. One could be positive, one could be negative. If I have that, I'm still keeping the limit notation because remember, we're not solving the limit. We're finding an equivalent limit that's going to be easier to work with. We have to indicate we're doing L'Hopital's rule. And when I get to an example, I'll show how we do that. And take the derivative of the numerator and the derivative of the denominator. And see, okay, let's start the process over. I now have a new limit. Let's try substitution. And we could actually be asked to do L'Hopital's rule a couple of times before we get to something where we can say, yes, it's going to be approaching this real number, or no, this limit doesn't exist. So you just keep repeating this general approach until substitution works, or you're unable to use L'Hopital's rule. So an example of this is the limit as x approaches 0 of sine of x over x, which we did way back at the beginning of the course when we first looked at limits. And I said, this is just a nice limit to know because we see it on a regular basis, but it's also an easy limit to forget. So if you do, here's a quick way of evaluating this limit without actually having to look at the graph, which is what we did before as we graphed it. So I'm first going to try substitution. And when I do that, when I substitute into the numerator, I have the limit as x approaches 0 of sine of x is approaching 0. And the limit as x approaches 0 of the denominator, x, is also 0. So this right here shows the limit is approaching the indeterminate form of 0 over 0. Do not write that it equals 0 over 0. It is okay if you were to say, well, this limit approaches, by using an arrow, 0 over 0. That is acceptable, but if you use an equal sign has a very strong meaning. And you're saying it equals whatever 0 over 0 is. And we can't ever find that, so you'd be saying right off the bat the limit doesn't exist. So do not use an equal sign. So now that I've shown that I have a 0 over 0, I now indicate that I'm going to use L'Hopital's rule. And the easiest way to do that is to draw an arrow to the next step. And we'll mark it L'H for L'Hopital. I then need to write my limit notation still, because I haven't evaluated the limit. I am getting an equivalent limit. I am not doing the quotient rule because this isn't a quotient, this is a ratio. So I want the derivative of the numerator, which would be cosine of x, over the derivative of the denominator, which is 1. I now have a new limit. I go ahead and approach this as saying, okay, let's start by trying substitution again. If I plug 0 in for x, I get the cosine of 0 is 1. The denominator is also 1. So this is approaching 1 over 1. And there is our solution to the limit, because we have gone from our original limit to an equivalent limit to a real number.